Alright, the purpose for this video is solely for my students in my classes. Some of you who may be using my website or my YouTube videos for other purposes, maybe you'll get something out of this, maybe you won't. But the purpose for this is to go over the concepts in a really quick, straightforward way for the third exam that I give pretty much in any of my statistics classes that are based upon a 3-exam schedule. So I have a whole outline. You should go through the entire outline and see all of the things that are important. But I was thinking of how could I really bring these things forward. So here's what I decided. Number one, the first thing that you need to be able to do is to know the binomial distribution. Okay, knowing the binomial distribution, that is going to require you to know how to find binomial probabilities based upon the binomial distribution. So that was something that was tested on the last exam. But because I want to make a relationship between the newer material and the older material, I need to have this brought forth again. So you know that X is distributed binomially with some n, some p, and some q. That's a binomially distributed random variable. And I need you to know how to find the probability that x is equal to some random variable, let's call it 5. I need you to know how to find the probability that x is greater than some random variable. Again, let's use 5 as an example. And I need you to know how to find the probability that x is less than or equal to some random variable 5. This one is using the binomial PDF on your calculator, and I am just going to talk about this in terms of what you would use on your calculator. And you would put in your n, you would put in your p, and then you would put in 5. For this greater than one, you have to be able to rewrite this in terms of 1 minus the probability that x is less than or equal to 5, the direct complement of the greater than. And then this and this will relate to one another. In order to do a less than, you need to know that this is a binomial CDF, and we would have, in this case, the n and the p, whatever they happen to be, and the 5 would go in here again because it is the probability of less than or equal to 5. You need to know how to do that. Then we talk about, in these statistics classes, the normal approximation to the binomial. So the normal approximation to the binomial is rather archaic in today's day and age because our calculators do those probabilities that I just showed you. However, if something should ever fail with our calculators, or we shouldn't have a calculator, or if we want to try to make some relationships between what we do in confidence intervals, hypothesis testings, and relate it back to what we're doing under the binomial and see what's the relationship here, this kind of can make a link between the two of them. So we still teach this. So the normal approximation to the binomial, that's the next thing that you need to be able to do. And so what we'll look at here in the normal approximation to the binomial, first and foremost, you need to be able to do a continuity correction. So continuity correction, this was making sure that those bars are accounted for in a PDF for a density function, a continuous versus a discrete. So continuity correction is the next thing. Now continuity correction takes into account what we had in a binomial. So x binomially is distributed this binomial random variable, and then we're going to take it to being distributed normally. Now, under the normal assumption, these x's here, these are now assumed to have a mean n times p and a standard deviation of n times p times q. Remember that this is representative of our mean for the normal approximation, and this is standard deviation for the normal approximation. Okay, so if we had the original probability under a binomial that x binomially distributed is equal to 5, in order to do continuity correction, we're going to have to say that this is the probability that we have between 4.5 and 5.5 to be changing it to an approximation under the normal distribution. And if we had the probability that x is a binomially distributed random variable and it was greater than 5, well then the normal approximation would have to start out with the continuity correction that we're beyond that bar. So when we go to do the normal, we're going to start at the edge of the bar, 5.5, and go on up. And finally, if we were looking at the probability of a binomial random variable being less than or equal to 5, now we want to include that whole bar. So when we go to do it with a normal approximation, we have to do x being a normal random variable is going to be less than or equal to 5.5 as well. So what this does is it includes those edges of the entire bars that you see in a probability distribution function's histogram versus a smooth curve. All right, so that was the continuity correction. Now, once we have the continuity correction, then you have to understand that to find normal probabilities, we have to standardize, right? So to find normal probabilities, you standardize. And to standardize, the general standardizing process is to get a z-score, right? And you start out with the random variables value, and you subtract the mean, and you divide by the standard deviation. And so if we're talking about doing a normal approximation, this is where we're going to put in our n times p for the mean, and the square root of the n times p times q here, and these random variables will be the x sub n's that we were dealing with on the last page. And so that'll be standardizing, and then to find the probability of these z's being greater than some z value that we just came up with is table or calculator. And I've gone over how to use a negative z table. You will be provided a negative z table on this test so that you could use your negative z table in order to look these up, or it's perfectly acceptable on this test in order to use your calculator. And remember, on our calculator we do normal and we do CDF, sorry I should have written normal, and then we do the left endpoint, and then we do the right endpoint, and then that's all we have to put in because we're assuming the 0 and the 1. And if you have an older operating system, you don't have to put these in. You're just going to enter this one, and then you'll hit the return key at this point right here. If you have the newer operating system or the newest operating system on a TI calculator, it already has 0 and 1 put in, so you just enter, 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 and then it pops you out to your screen, and then you hit enter again, and it gives you the normal probabilities. So that's all you would do here. On the table, the tables, we always have to put things in terms of being less than some negative z-score. And once we do that, then we can find our table values. Okay, so that would be the link to what was tested on my second midterms in a 3 midterm class, because on the second midterms, I test you on how do you find probabilities of z's, right? So how do you find normal probabilities? And I make everyone standardize in my classes. That's where everything starts. So those are some of the most basic things. Now the second thing that we're going to test. No, it's not central limit theorem. Let me erase this. So the second thing that I want to test is I want to talk about inverse normals. So you need to know the inverse normal distribution, and you need to know the inverse t distribution. So inverse distributions. And what you really, really need to know from these inverse distributions is that this is using a probability to get back to a value from your distribution. So you use a probability to get back to a value from your distribution. So what you are going to start out with is some decimal over here, right? These are decimals, and what you're going to get back from the value from the distribution is you're going to first get back a z-score, because I make everybody deal with the inverse normal, standard normal, and then you're going to do that unstandardizing process if you need to actually find values under your distribution that represent these probabilities. So when I'm talking about this, I'm saying, okay, remember when we had this, and we're saying, okay, well, there's this value over here, and that is the highest 1% of the population. And so what value here represents the highest 1% of the population if my mean is some given value and my standard deviation is some given value? What value in the distribution represents that? And that's an inverse distribution. Now, if we are using the normal distribution, of course sigma is known, right? So if it's the inverse normal that we're using, then we're going to be talking about sigma being known. But if we don't know sigma, then we're going to use an inverse t. And the inverse t, this is when only the sample standard deviation is known. And the way that we're going to use these later on, and that's what we've been studying for a couple of chapters at this point, is we're going to use these things in order to study our critical values. So the reason for using an inverse function is critical values. So let me put this in red. Critical values. And critical values are what we use in both confidence intervals and in traditional hypothesis tests. And so I'll put that. So we have two uses, right? And those two uses for critical values, number one, they are used in the margin of error. Computation inside a confidence interval. And the second reason we use them is a traditional hypothesis test. And there is a link between confidence intervals and hypothesis tests, and we see that link when we study how to do a hypothesis test using a confidence interval. So those are the reasons that we need to know those. And I can test this inverse function just directly as can you use a probability to get you back to a random variable under a certain distribution, and I'm also secondarily able to test you on this based upon your ability to find critical values when you're doing a confidence interval. And the confidence intervals are the very last thing that we're going to study going to have tested in the majority of it for this particular test. Now I'm almost out of time, so I'm going to do yet another video, and I'm going to finish up the two last things that you can see on this test. So let me in for now, and I'll come back in a second.